Okay, so let's get started. How many of you have read the assignment already? Okay. So before we move on to the code, I'll just go over some notes on how to go about this assignment. I think part of it has already been covered by Gerald in classes 2 weeks back. All right. So there are slight differences from what has been taught in class and what we're doing in this particular project. The main difference, number one, is that you're doing a 4-byte aligned block, whereas I think in class they taught you 8-byte aligned. And the other difference is that you have a pointer to the next block, which I believe was not there when Gerald taught in class. So for the purpose of this assignment, you'll have to note these differences. Okay, so if you look at a sample heap block, this is how it's going to look like, right? You'll have the block header, which is going to contain the block payload size plus the padding size, which is this and this together. And then you have the pointer to the next block, which follows this whole block, right? So the last bit in your, this is going to be your size status. So the last bit is going to indicate if this particular block is free or allocated. So if it's going to be 1, it's allocated, and if it's 0, it is free. So the block size is nothing but your payload size plus this padding size. Why do we need padding?
What were the questions?
Why do we need padding here?
Because not enough space at the end for another new block to be free.
Okay, I mean, if we need it to be 4-byte aligned, right? So if it's not going to be 4-byte aligned, you need to add some bytes to make it the whole one 4-byte aligned. Okay, and right, so this is going to be the block size, these two together. And then your block header size is going to be this plus this, right? Which is the block header. And that is going to be 4 bytes for the block size and 4 bytes for the next pointer, these two. So pointers are 4 bytes, and this is going to be an integer, so it's going to be 4 bytes as well. So it's totally going to be 8 bytes for these two together. So the minimum total block size is going to be this entire thing, which is 8 for the header, and which is going to be a minimum payload of 4 bytes, right? Okay, so I hope you guys are familiar with these diagrams of how all these what these numbers indicate. So initially you have, as we discussed here, we have 8 bytes for the header, right? So these two are going to be together 8 bytes, because remember it's 4-byte aligned, so each of this box is going to be 4 bytes, right? So this is 4 bytes and this is 4 bytes, so this together is the header. The first 4 byte, as we discussed, is going to be for the size, and the next 4 byte is going to be for the pointer, which is next. So why do we require pointer here? This pointer is nothing but it points to the next block, next heap block, right? So this is something different from what we taught in class. So basically this is going to be your header, these two together, and this is actually your payload plus padding, right? Here we said that it is 8/1. 8 indicates that your block size is 8, so it's going to be 4 bytes plus 4 bytes for this, which is going to be 8 together, right? And then you have /1 because it's allocated. The last bit is going to be 1, so it's allocated, so that's why it's shaded in, it's kind of crossed out saying it's allocated. Does that make sense?
Yeah, so just a couple of points of clarification. One, sounds like we are linking all the allocated and the free blocks.
Right,
So
right.
not just the free block.
Right.
Okay, so
Right.
that's one. The second one is also,
Right.
I guess, I thought from the specification it looked like we were supposed to, the size of the block is essentially just the size keeps track of only the, does not include the header, right? Size keeps track only of the
Yes,
padding,
yes,
padding
yes,
is what
yes.
I recall.
Yeah. So the size here is basically given as 8 because it's 4 plus 4 of these two blocks, right? So it does not include the size of the header,
I see.
right?
Okay.
Was that how it was taught in class?
No, in that class it was a combination, it was the header held the size of everything.
The header including the payload. Okay, okay. So I think number one difference would be that. I think it's explained in the mem.c as well as in the doc. Okay. All right. So that's one difference. And then when we go on here, it says it's going to be 4 bytes of the rest of the block, and it's going to be these two are headers, right? Again, 8 bytes is for the header. So this is the first 4 bytes is for the block size. The next 4 bytes is for your pointer, which points to the next block here, right? So all these pointers are indicated by dots, and the pointer is pointing to the next block that is there. So the pointer would point after these many number of bytes, which is 8. So after 8, which is the block size, it would point to the next one. After 4, so after 4, it would point to the next one. Now this is 8, so after 8, these two together, it would point to the next one after it. And now this is 12, so it's like 4 plus 4 plus 4 plus 4, 4, 3s are 12. Okay, yeah, so these two is for your header, and then these 3 is the actual block, right? And it's 0 because it's free, and this again 0 because it's free. Yes?
Are we not tagging the end with that 0/1?
The end
The
with...
end of the if block where the
Right. I think it is not mentioned in the doc as well as the specifications, so you don't have to do that.
Okay, so it's basically considered another free space as the very end.
So the null pointer would indicate the end.
Because I think from the class it is only for the free list maintenance you have the block, the 0 1 block at the end, you mark the end. But in this case they're using a link constructor and showing how we do.
Yes, so you would, null would indicate that you traverse through the entire block. Okay, so this is going to be your list head. So this would be initially, if you look at the code, yes, so initially this is given as null, right? List head is given as null. So you have mem init here, and memlock, which you would be writing, memfree, which you would be writing, and then memdump is also provided for you. Okay. Alright, so this is how the structure looks like. You'll this is the block header, right? You have a pointer to the next block, and as well as you have the size status, which is going to indicate the size of your block here, which does not include the size of your header. Okay. All right.
Planning to put this PDF on the site after you're done?
Yes.
Okay.
No, I was planning to write it down, but there's no doccam here, so I'm not able to write it down. Okay. So initially you would have it to null, and then looking at the placement of allocated blocks, I hope Chiral has mentioned about best fit, worst fit, and first fit. So you would be implementing all of those in your program. So for example, we'd be, if it's going to be best fit, we are going to look at like malloc s, which is starting from the first block, you will choose the smallest free block that fits ES bytes, right? The amount of bytes that's left over should be minimum in best fit. Okay, so example for this. So if you look at the structure, what we have is we have 8 bytes of free memory here, and then we have 4 bytes of free memory here, and the rest are occupied or allocated, right? So when you ask malloc of 4, it's going, there are 2 options here. One is block 2, which is 8 bytes, and one is block 4, which is 4 bytes. So according to best fit, which one would you choose? The 4 bytes one. If it was worst fit, which one would you choose? 8. And first fit? 8. Great. Okay, so we would choose B4 for malloc of 4. All right. So, you know, whenever you're going to do this malloc, be sure that you change 2 things always. You have to change your size status, indicating that it is allocated now, right? Once you make it allocated. And you'll have to set the next pointer. So there's a special case which I think I'll be covering, splitting free blocks. Yeah, right here. So this is a special case you have to handle in malloc. So for example, let's say you have 16 bytes of free memory here, right? The block is 16 bytes and it's free because it's /0. And the next is pointing to another allocated block here. Okay, so now when you say malloc of 4, what would happen is, let's assume this is what is returned by the best fit or whatever fit it is. And we see here that we have 1, 2, 3, 4, 16 bytes and we just need 4, right? So if you look at this, we have 4 bytes which are allocated, indicated by 1 here, and these 2 are the header. So this is the 4 bytes which we allocated, and then the rest can be classified as free block now, right? So that's going to be a header of 8 bytes right here, and this is the free block of 4 bytes. So this was possible because you had enough space for you to bring in a header as well as a 4 byte payload, right? At the same time, if it is going to be malloc 8, what would happen is these 2 would go for payload, which is 8 bytes together. This was of course your header, and then you just have 8 bytes remaining, which you can only use for a header. You don't have a payload there, right? You basically need 8 bytes for the header plus 4 bytes for a minimum payload. So you would not split in this case. This would just be a padding in this case. So you have to handle this as well when you come to malloc function, implementing malloc function. So in this case, you have to be careful of setting your next pointer, right? The next pointer that we saw. In the block header, initially it would have been the next pointer would have pointed to the next allocated block here. Whereas when you decided to split, you should change the next to this block here, and the next of this block also has to be set to be equal to the previous block's next, right? But if you're not going to split the block, you don't have to change next because it's going to point to the correct next, right? So you have to handle all these cases and modify your size status as well as your next pointer. Okay, now let's look at coalescing free blocks. So there are 2 cases we have to handle. The assignment doc mentioned that you have to coalesce free blocks which are present both behind and ahead of the current block if it's going to be free, right? So let's look at both examples. So case 1, let's assume the pointer P is going to point to this payload here, and this is the header for that payload of that block. It's going to be 4 bytes, so we have 4 bytes, which exactly 1 box here, and it's allocated. Ideally these should have been shaded, and then you have 4/0 because this is going to be free, and this is just 4 bytes, and this is your header for that block. So if you look at P right here, we see that the next block, which is this, is free, and the previous block, which is this, is allocated, right? And when we say free P, we are basically going to free this particular block, right? And when you're going to free this block, the entire thing would be free now. So you have to coalesce the entire thing, and you have to change the size status right here to 16 instead of 4 which you had before, and you have to modify the next pointer to point to the next allocated block. So basically you're getting rid of this, right? Okay, and in case 2, it's just the exact opposite of this. Previous block is free, and the next block is allocated, right? So if you look at P here, it's the same thing. You have the previous block, which is this, which is free, and then the next block, which is this, which is going to be allocated. So again, it's 4 bytes of free block, and then 4 bytes of allocated one, right? So when you say free P, it would free this, and now these two would get combined, and it would be 16/0. Do you have any questions in this entire thing? I'll post a link on the website so you can access this. But this kind of shows you an overall picture of how you would be doing your malloc and free implementation. Sounds good? Okay. Now let's go to the terminal. Let's look at the sample skeleton code that was given to you for mem.c. Do you want me to minimize the background, or is it's see-through? I'll probably minimize that. Give me a sec. Okay, so this is the structure we just saw right now in the doc. So we have a block header. This is going to be the header for each block that you're going to allocate, right? And this has a pointer, which is next. And so the blocks are maintained as a linked list, as we saw, and they're ordered in the increasing order of address. The size of the block is always a multiple of 4, as discussed. So we're going to have multiples of 4, right? Which is the end byte would be 4 or 8 or C. In that case, the last two bits would always be 0, right? In 4 it is 100, in 8 it's 1000, and in C it is 1100. So the last two bits are always going to be 0. So we would use the LSB, least significant bit, to indicate if it is free or allocated, as discussed before. Okay, so this is important. So for a free block, the value that is stored in size status will be the same as the block size, because the last bit is going to be 0, right? And for an allocated block, the value that's going to be stored in size status will be 1 more than the block size. That's because you have in this line we've indicated that LSB is going to be 1, right? So it's going to be +1 over there. So if you want to know the actual size of that particular block, you would do the size status -1 if it's allocated. Okay. The value stored here does not include the space required to store the header, which was not the case as discussed in class. It's a bit different here. So to see an example, for a block which has a payload of 24 bytes, you have an additional 8 bytes for header, right? Size status would be set to what? You just have a payload of 24 bytes. So size status does not include the 8 bytes for header, so it's just 24 plus 1. The +1 is because you have to have the LSB set to 1 to indicate it's allocated, right? And if the block is going to be free, you would just say 24. You wouldn't add that +1 because LSB is going to be 0 anyway. So this is just an example of this 2 lines that was explained before, right? So for free block, it's just size status, which is this in size status is just going to be the same as the block size, whereas for allocated block it's going to be 1 more than the block size. So this is exactly what we saw, which I explained in the doc, where you have a pointer as well as an integer to mention your size, right? So this was the one that was taking 8 bytes, 4 bytes for your pointer next and 4 bytes for your size status. Okay. So here we are maintaining the list head, which is going to be null initially. This is a global variable, and this is always going to point to the first block. That is the block with the lowest address. So now we have filled up two functions for you already, which is meminit and memdump. So meminit will be initially called once by the program, so that you can request enough memory to be allocated, initialized during the first call to this. For example, if I'd say meminit of 4096, it's going to allocate that many number of bytes. So we would see how it's done in this. That's basically using mmap function that we get this bytes allocated or initialized for our use. So there are two arguments here. Argument 1, which is going to indicate the size of region, which specifies the size of chunk which needs to be allocated. So whenever you call memalloc, it would be allocating bytes from this entire size of region that you're allocating first, right? And this is just the size of the entire, let's say, the heap you're considering, right? And it would return 0 on success, and it would return -1 on failure. I think I did not explain what, give me a sec. So for policy is nothing but whether it's going to be your best fit or worst fit or first fit, right? So this indicates the algorithm to use, or let's say policy to use. How does Gerald Edler call it? Example, best fit is 0. Okay, so I believe 1 is first fit and 2 is worst fit. It was mentioned in the doc. Okay.
Mention which one is which. It just says best, worst, or first fit.
I'm pretty sure I mentioned that. Let me just pull that up for you. Where is it? Yeah, so right here. Probably I would make that bold after I get back so that it's visible. I mean, it's easily noticeable. Okay. All right. So once we indicate the policy here, note that this would be called only once, right? So once you set the policy to be best fit, all the malloc that comes after that is going to follow best fit. There's not going to be a combination of both in the same thing, right? So because meminit is just going to be done once, you're just going to grab an amount of memory for your mallocs, right? So it's just going to be done once. So that's why we have a static int allocated once, and once we do meminit, we'll set that to 1 so that we don't keep on doing meminits by mistake. Okay. So there are a couple of variables here: page size, pad size, allocated size, and so on. So if your allocated once is already set to 1, it means that you've already called meminit, so you wouldn't do it. So you would say meminit has already allocated space during a previous call. And size region is nothing but your argument, which indicates the amount of space, overall space you want, right? So if it is less than 0, it doesn't make sense, so you would say it's not positive. It has to be greater than 0. Page size is going to be from your unistd.h, which is a system call to get the page size that the system is following. So there was a part in the doc which explained about page size here. Let's see. page. Yes. So whenever a process is going to ask for memory, the operating system allocates memory in terms of pages, and it's going to be the smallest unit of data for memory management in a virtual memory OS. So there's a link if you want to read more about pages. So for the purpose of this assignment, you don't have to worry too much about it, just the fact that this would be called once in this entire program. So you get to know the page size, and then what you would do is you have to make the size of region, which was passed as an argument to this function. You should round that up to be a multiple of page size, because the OS just gives you memory in multiples of page size, right? So this is the calculation to make it, to round the size of region up to a multiple of page size. So finally, this is the size that you want to get, which you will pass as an argument into mmap. So we are using mmap to allocate memory. Let's look at the system call for that. Man mmap. So it creates a new mapping in the virtual address space of the calling process. The starting address for the new mapping is specified in address right here. So we passed it as null. So if it's going to be null, then the kernel chooses the address at which to create the mapping. So that is, we're not specifying anything. And then the length is going to be whatever alloc size we defined in the previous line in our code. So and then you have something called prot, which is going to be the prot argument. It describes the protection of the mapping, whether it has to be read only or write, it can be written or it can be executed, and so on. So in our case, we want to set it to be both read and write, so we would set both of this. And then I think we go with map private. So this mapping is not visible to other process mapping to the same file. Again, you don't have to worry much about it. You don't even have to know about it, given that it's just called once in this entire program, and that was already given to you. So mmap basically creates that amount of space which we defined here, right? And it's going to return a pointer to that. And if the return value from mmap is going to be map failed, it means that it cannot allocate any space. And we set allocated ones to be equal to 1 because we don't want to repeat memInit. So initially when we start off, we are just going to have one big free block, right? So you would have to set the next to null. And you have to set the size status to be equal to the alloc size, which we defined here, minus the size of the block header, because the block header size is not generally included in your size status, right? And what we are doing here is we are setting the fit to be equal to policy. Fit is something that is a global variable right here. So whatever policy we are getting, whether it's 0 or 1 or 2, we're going to store that in fit, because you can use fit in your, let's say, where is your malloc? You can use it over here in memmalloc to decide whether you should follow the best fit or the worst fit or the first fit policy, right? So memInit gets that argument, you set that to a global variable so that you can access the global variable to decide if you have to do one of these policies. Okay, so next is going to be your memalloc and memfree, which you guys will be implementing. So this is the function for allocating size bytes, which is similar to malloc, which you guys have been doing in your program so far. So this returns the address of the allocated block on success, returns null on failure. check for sanity of size, return null when appropriate. So if your size is going to be greater than the allocated size you got in your meminit, you have to return null, right? And you have to round up to a size of to a multiple of 4, because we already discussed that it's going to be 4-byte aligned, right? And you'll be traversing the list of blocks, all the blocks we saw in the linked list, one at a time, using the next pointer to allocate the best free block. So when I say best free block, it's not best fit, it's just the best free block with respect to the particular policy, right? Which can accommodate the requested size. So this particular line, which talks about when allocating a block, split it into 2 blocks when possible, right? This is basically what we saw as the sample case when I was discussing in the doc. If you have enough space for header, which is 8 bytes, and a payload of minimum of 4 bytes, which is totally 12. If you have at least 12 bytes remaining in that block, you would split it into allocated and free, right? Otherwise, you would just have it as padding throughout the entire block. Okay. So if you look at memfree, this is going to free up a previously allocated block, which was allocated using memalloc right here. So the argument is going to be the address of the block to be freed up. It returns 0 on success, returns -1 on failure. So when is it going to fail? If the pointer is null. You cannot do free on null, right? And also if pointer is not pointing to the first byte of a busy block. So this pointer is basically not pointing to the header, rather it's the pointer to the first useful byte in that block, right? So it should point to the first byte of a busy block, not a free block, right? Because you cannot free a free block, which is not defined. Okay. So once you do that, you have to mark the block as free, right? So in memalloc as well, you should mark the block as allocated in the size status, right? And last but not the least, you have to coalesce if one or both of the immediate neighbors are free. That is, if either the previous block or the next block is free, you'll have to combine those. So we saw 2 cases of this in the doc when I explained it. Okay. So if you look at memdump, this is basically a function given to you for debugging purposes. So you might find it useful to do a memdump after every memalloc, for instance, to see if it's being allocated to the right spot. So this prints out a bunch of information, which is like the status, which is free or busy. It gives the address of the first useful byte in the block, which is the byte immediately after the block header, and then it has the end, which is going to be the address of the last useful byte in that block. Size, which is the size of the block excluding the header. T underscore size is going to be including the header, and T begin is nothing but the address of the first byte in the block. This is where the header starts, right? So T begin and begin is just different because begin does not include the header. It's just the first useful byte in the block. So what I mean by that is, if you look at this, this is the first useful byte in the block right here, right? Whereas this is the first byte in this block. This is the block. This 4 boxes together is the block. These 2 boxes are the header, and these 2 boxes are the payload plus padding. So when I say the first useful block in the byte, this is the first useful byte in the block, and this is going to be the first byte in the entire block, including the header, right? Okay, so that was what was mentioned here. So you have a counter to show which block it is, and then you have a T begin size, T size, and free size, busy size. So you'll keep track of how much amount of memory is free and how much amount of memory is busy. For example, it's just adding up all these stuff, right? So here you have 4 bytes of free memory, here you have 12 bytes of free memory, here 8 plus 8, 16 is busy. Okay, you initialize all that to 0, and you keep on adding stuff here to the total size and the free size here. So when you execute this, it's going to print out a very nice table for you, which is going to indicate all of these variables. So for example, tBegin is initially set to be equal to current. Current is your list head, which is the first block in that entire list, linked list. And tBegin is the first byte in the block, right? And begin is nothing but the first useful byte in the block. So you would move it by 8 bytes, which is the size of the block, to get the actual useful byte of the block. And size is nothing but current size status. How do you find if it's a busy block or a free block? When you AND it with 1, which is nothing but ANDing with the last bit in that size status which you said. If it's going to be, if you AND it and you're going to get as 1, it means that it's allocated. And if you AND it and it's going to be 0, it's going to be free. Hope that makes sense. Okay. So if it is a busy block, we know that the actual size is size minus 1, because this 1 was actually added to it to indicate that it was allocated, right? Minus 1 for ignoring the status in busy block, and then t size would be whatever size you have plus the block header, because that's how we defined it. It's going to include the same size including the header, right? So that's why we add the header here. And then this is busy block, right? This one is busy block, and hence we are adding this size to the busy size, whereas in this else statement it is a free block, so you would add that entire size to your free size, right? And end is actually the byte at the end of your linked list. It's going to be begin plus size. So begin was the first byte in your block, plus size of the block would give you the end of that particular block. Okay, so all this is going to be printed out to your screen here, and then you would say total size is equal to total size plus, basically you're keeping track of the total size through each run in this while loop. So you would know up to that block how much size you have, right? Okay, so you have current is equal to currents. Next you're moving to the next block, and then you're incrementing the counter, because you'll be printing the counter to indicate which block it is. And then at the end you would totally print out what is your total free size, total busy size, total size, and so on. So that's pretty much it. If you look at mem.h, we would have defined, given the signatures of all these functions that we have. So do not modify this. Never modify the function signatures of these 4 functions, because we'll be using it for testing. So there are a couple of tests that are given. This is how we'll be writing tests to check your program. So if you look at align, it's going to check if it is aligned to 4 bytes. If alloc, it checks whether you're able to allocate using the memalloc function. Alloc no space is like if there's no space in the heap to be allocated. For example, you give a larger size than what you allocated using memInit, what would happen? It should return a null or whatever was mentioned on the specification. This is an example for best fit, first fit, worst fit. Writable is nothing but can we write something to the block which you just malloced, right? Remember we did a proc, I think prot underscore write and prot underscore read in your memInit. That's because you want to be able to write in those blocks. Yeah, free.c does your program support memfree. Right, so I have not completed this function, so once you complete all of this, this shouldn't be there. Make them. Okay, any questions?
In the mem.c file, will you give an example of the size? And you mentioned it was 25,
Yeah.
I can't figure out where that one byte is coming from.
Oh, that's because LSB is 1, right? So you would have the last bit to be 1, which is basically incrementing it by 1, right?
Oh, okay. I see.
The last 2 bits wouldn't be, would always be 0 because it's 4 byte aligned. So the last byte would only be like 4, 8 and C, which is so the last 2 bits in that is always going to be 0. So you use those bits to indicate whether it's allocated or free. It be 1 or 0. If it's 1, it means that you're actually incrementing the size by 1, right?
But I thought the least significant bit is the size value in the header, so it's not included in the payload component. Or am I not understanding this correctly?
So the size status, so we are talking about the size status here, right? The LSB in the size status, right? So the size status is the actual size of your payload. It doesn't include the size of your header,
Right.
right? So when we say payload is 24 bytes, you have 24 bytes. But if you wanted to include the header, you would say it's 24 plus 8. And then again plus 1 to indicate it is allocated. I mean, does that make sense to others?
Maybe I'm just confused.
No, it's just that maybe I should have explained it better. I think it's when I say for a block the payload is 24 bytes, I'd have to put that 24. I have to indicate that the size is 24 bytes, right? So I use size status to indicate it's 24 bytes, but I wouldn't include 24 plus 8 because I'm not going to say I'm not going to include the plus 8 for the header because I'm not going to say that. I'm just going to indicate the size of the payload, not the size of the header plus the payload.
Right.
But at the same time, I have to do a plus 1 because I have to indicate that it's an allocated block. Because if the least significant bit is going to be 1, it's essentially adding the value by 1, right?
Okay. Yeah, I think I get it.
Okay.
Least significant byte of the size.
Least significant bit.
Sorry.
Yeah.
Least significant bit is incremented by 1, so the actual value of it is actually 1 higher than.
Yeah, yeah.
If you're looking at buckets on page 821.
Sure. No, I think I just couldn't figure out. I was actually thinking about the physical size of 24 versus 25 rather than the actual value that's stored the size of. And I think that's where I got a bit confused. Like you're not allocating 25 bytes of payload.
No, no,
You're
no.
allocating 24.
Right.
But saying the value of the size is 25 because the least significant bit increments it. by
Right,
1.
right. You're right.
I think that's where I got confused.
Sure.
This is more of a syntactic question that I noticed with when you were going through, I think, like men in it or in front of those functions. Why do in those, like typically I've seen this in other instances as well, for those type of conditional comparisons, why do we do the constant before the variable? I've seen that convention on a couple of occasions, like 0 not equal to allocated ones as opposed to the other way around.
Right. I think, I mean, I have come across this in some examples where the allocated space, allocated ones, for example, that variable is null, or if it is, I don't know, not defined as something like that, it wouldn't make sense. But in this case, I don't really think it makes a difference.
I mean, the only thing I was able to think of is if you stick to this type of convention, accidentally doing an assignment in an equal, condition.
Yeah.
You probably avoid
Yes.
that situation.
Yes.
But I don't know of any other reason beyond that.
Yeah, I think that is a very good reason. Yeah, I've come across that too, to avoid accidental setting of the variable to be equal to that value. Yeah. Any other questions?
Can we add private functions, like a split function or cola?
Yeah, you could write whatever functions you want, but it's just that you shouldn't change the signature of the existing functions.
And is the general idea of writing for this assignment to the extent that the consumer will probably put the header in their, use a header in their program to consume the functions that we are writing, right? That's the general nature of how we are writing.
As in the consumer, as in
some other program would be the consumer of our functions who's writing it.
Right. So in the test, that's what we're giving as example, right? There we are giving a call to all these functions here, so that we allocate do memlock and memfree using this program.
And
yes.
we don't have to worry about like the SBRK
No.
pointer or anything like that.
No. So what we use here is just the mmap, which you don't have to worry about because it's already given for you, but you just understand what it's doing. That's about it. Any other questions?
How large is the program in comparison to what program 5?
I think it's not too big. I mean, program 5 was basically like you had a lot of if or switch cases to compare. This is not going to be that hard. It's just like 2 cases you have to handle, right? In free, it's like coalescing the things before and after and setting the size status, and for your memlock, it's basically setting the size status as well as deciding if you have to split it into allocated and free. That's about it. So I think it should be like maybe 20 lines of code for each. I mean, if you can write it in an optimal way. I think you can work with a partner for this project, so it would be more easier than the previous ones.
The last function has a line that's more than 80 characters, I think.
What's that?
Well, one of the last lines is longer than 8 characters, which is one style.
Oh, this one?
Yeah.
Yeah, that's true. I'll fix this. Thanks for pointing that out. Any other questions? Okay.